Hello, programming languages students. Welcome back to another grammars video. For this one, we're going to talk about we just finished some examples, got basics of grammar rules, and so we're going to talk about grammar notation and some things that grammars can do that other tools we've used before cannot. So first, for general definition of grammars, we're going to focus a lot on the production rules. That's the main interesting part to us. But it's important to know that when you define a grammar, you also have to provide really clear information about the full list of variables. So for us, these are the capital letters we're using. These are our rules. You also need to provide a full list of the terminals, the ways that your language can end. And then you also need to specify your start variable and then your rules. So like I said, we're going to focus on rules. But real quickly, what do these things look like in practice? So list of variables or these list of rules. An example in Java is that modifiers rule. Um, so if you define modifier as a rule or a variable, then you would also have to define terminals for that rule. And so a modifier might be public or private or static, right? So the full list of terminals, the full list of modifiers is available out there for Java as part of the grammar. And so you also have to define a start variable, which you could go look up in the Java language. For us, we're always going to use s. And so these are things that are important to define. We're going to kind of make some assumptions about the rest of these and just define production rules. So this is the part we've been writing. These are the rules that the grammar has to follow. And so we're going to focus on this, but it's important to know when reading grammars that all of these have to be defined for every language. So let's talk about the theory of grammars. Grammars can actually cover, because of the flexibility in writing rules, they can cover a wider range of languages than automata. And so there are actually two classifications for languages that can be generated by grammars. There's context-free and context-sensitive. We're going to focus really heavily on context-free um, because there's not a ton of situations where context-sensitive shows up. And either way, it's beyond the scope of this class. So we're going to focus on context-free. And so what things are part of a context-free grammar or context-free language? Well, let's go back to maybe one of the first problems that we ran into with automata, where we had a problem that we cannot solve with an automata. So this is language a to the n, b to the n. Note they're the same variable where n is greater than 0. And the trick here, the reason a finite automata can't draw this or represent this is because um, we have to count a potentially infinite number of a's and match that count with a potentially infinite number of b's, which would require an infinite number of states, which means we're no longer a finite automata. So we can, however, define grammar rules for this. There are production rules that allow us to write this language or create this language. So why don't you guys take a shot at it? You can pause the video if you'd like. I'll give a few seconds here for you to pause it. Give a shot at some rules, and then we'll talk about the actual solution. All right. So here's the solution. Um, it's one rule. Turns out it's not very complicated. S is substituted with A, S, B, or AB. So if we choose the first substitution, we get 1A, 1B. If we choose the second one, and note the order matters here, we get a lowercase a, and then a substitute for an s, and then a lowercase b. So if we do after one loop here, substitute AB in the middle, we get AABB, because this substitution is going to happen in the middle of our word. And so really what we're doing is building this word out. And the key is, when you define a grammar rule, you can add things at the same time, which guarantees that these things are put in the same numbers. There's no way to use this rule to produce a different number of A's and B's. So this is not a regular language, but it is pretty easy for a grammar to define a rule for this. Um, and so we don't have to count. Instead, we can just add things at the same time. And so a to the n, b to the n greater than 0 is not a regular language, but it is a context-free language. So it's important to note that every regular language that exists is context-free. Anything that you can create with an automata, you can create a grammar for. And we'll talk about how easy it is actually to do this. But not everything that you can create a series of grammar rules for can be drawn as automata. So context-free, not all context-free languages are regular, but all regular languages are context-free. We're also going to talk about context-sensitive languages and what that means in an example coming up soon.